So it's a pleasure to close this conference, actually. Yeah? And as usual, happy birthday to Jonathan, Lisa, and Elle. And it doesn't work. Okay. So this is special for Elle. We met in 2002. Was my first trip to Israel, and this is a stamp for the visit permit for entering Israel at this time. So it's a 20-year story of friendship that I'm very happy to celebrate with you. Okay, so my talk is about a cleaning job. This is a cleaning job, so I want to motivate why I feel important to do symplectic diffeology, to extend symplectic geometry to something a little bit bigger. And symplectic geometry deal in general with symplectic manifold. What is here? Symplectic manifold, pre-symplectic, but as you know, and we had an example just before, that sometimes there is the infinite dimension space involved, or before, or singular reduction, etc. So there is a lot of situations where symplectic manifold are not enough. We deal also with groups which are not necessarily Lie group, with infinite dimensional, or even not Hausdorff group. And I will show you some situations where we have a group, we involve groups which are not Hausdorff. And we can do some geometry, and the reduction, the symplectic reduction, as you know, introduce most of the time quotient space that are not manifold, but they still carry a parasymplectic structure. Parasymplectic means just a closed to form, because I need a word to say closed to form. I want, let M equipped with a closed to form, etc. So I just want to have a word, a special word to denote that. And I will try to show you how diffeology can be a uniformizing framework. So the question I was interested as a priori, so I will go quite fast because you see I have 58 slides and I have 50 minutes. So so I have to be fast. So let's look at a few examples of where we need something more than symplectic geometry. So, for example, you have this moment of imprimitivity on the cotangent of a manifold, but the group acting is a group of the abelian group of smooth function, and the action of a smooth function on Q and P is just Q. You don't move the point, but you add the differential of P at the point Q. And this action preserves this form, the standard form. And what is a moment map? Okay. The second, we just show a very nice and big and profound talk about this kind of problem. And so you talk a surface, an oriented surface, and you consider this two form, linear two form, bilinear form. And you have an action of three groups. The abelian group, you just add the differential to a form. The diffeomorphism, you must just act a diffeomorphism on the form. And the group, the space itself, which is a vector space, acts onto itself by addition. So, and this all action preserves this form, this bilinear form. So the question is, in what sense omega 1 sigma is symplectic space? So just say that this is symplectic space, but maybe there is something to make more precise. I just say, okay, it's a bilinear form and there is no kernel. And I will discuss this point. And of course, the moment map for this example. A simple example, the two torus, omega two form of the two torus, the push forward of dx dy. T2 is a group and act on itself preserving omega. The action of the group is just by multiplication or addition. What is the moment map for a non-Hamiltonian action, for example? We shall also answer this question and can generalize to any quotient space where K is a discrete subgroup, but discrete in the diffeological sense, not discrete in the topological sense, mean equipped with a discrete diffeology. So even if it is dense subgroup, it is discrete. Okay, Q in R is discrete, diffeologically speaking, not topologically, but diffeologically speaking, Q in R is discrete. two forms of an orbifold, so this is also a good playground, you know. An orbifold is locally a quotient space of Rn by gamma, where gamma is a finite subgroup of GLN. We have two examples, a lot of examples, but among all these examples, we have the cone orbifold, which is a quotient space of C by the root of unity, or the corner orbifold, which is the product, the square of R over plus minus 1. So the question is characterizing the two forms on QM and omega QQ and group action and moment map. Same kind of question, same kind of question, but not same kind of space, okay? The space of geodesic trajectory is also a good example of application of this generalized diffeology. So you consider the Riemannian manifold, and the tangent space is equipped with a symplectic form, standard symplectic form. So it's a derivative of the Cartan form, the scalar product according to the metric with a vector and the variation of the point. So this is a serious notation, so don't be afraid of that. This means just vectors, the tangent vector, okay? The delta is just a prefix to denote the tangent vector at the point x. And the space of geodesic trajectory is, so these are the parameterized geodesic. The space of geodesic trajectory is a reduction of the unit tangent bundle. In the case of it is Riemannian. When it is pseudo-Riemannian, it's more complicated, but it's something else. And Eva told a little bit about that. So you have to reduce the unit tangent bundle, the symplectic reduction, by the geodesic flow. And when the space of geodesic is a manifold, when the reduction is a manifold, then the quotient, then omega pass to the quotient is symplectic. The geodesic of S2, for example, is an example of that. But what about the reduction in general? For example, when M is equal to the 2 torus, we know that the 2 torus doesn't work the same. Now, another example, in infinite dimension, you take the quotient of the infinite space, the Hilbert space, by the action of S1, and you have the infinite dimension projective space, and the reduction of the alpha, the moment map according relative to the action of the linear unitary transformation, etc. In one sense, the projective space is symplectic. Same question. The question are always the same. The moment map is that symplectic, and is there a moment map? This is a quite standard question. So this example is more interesting. This is an implementation of the Virasoro group. You consider the immersion, the space of immersion of S1 into R2, and you consider this one form. So this one form, you see this quotient, you divide by the speed of the path of the loop. You know, you are a loop in R2, you divide by the loop, the speed of the loop, and you take the product with the acceleration of the loop by the variation of the speed. This one form is not invariant by diff S1, but its derivative is invariant. So this is the action of diff S1 by reparametrization. The derivative is invariant. So what's the moment map? Is it equivariant? Actually, it's not equivariant. What is a Soryokov cycle? So the lack of equivariance, and is there symplectic reduction? And this is an implementation of the Virasoro group. Another example, reducing the complex periodic function. So you consider the periodic function on C, you develop this periodic function into the Fourier coefficient, and you have one form, and the standard one form and Fourier coefficient. Its derivative is just the pullback of the standard 2 form on C, on the complex number, pullback by the orbit map, by the value, value application. You see, x hat of f is just f of x. And now you consider the group R acting on E by multiplying each coefficient by exponential 2i pi alpha n t. So this is an induction of the ray line into the infinite product of torus. And you take the alpha n independent on Q, and now you have you want to reduce so this preserves the form, this action of R preserves the form, and you want to reduce the symplectic, the form you have, the parasymplectic form you have, along the sphere, which is a pre-image of the value 1 by the Hamiltonian of the action of R. So symplectic reduction, the standard symplectic reduction, and etc. You can add a lot of problem, a lot of situation where symplectic geometry has not is not developed to solve this kind of question. Okay, so now I will explain you diffeology framework. So yesterday, David cut the grass under my foot because he explained already what is diffeology. So I will not explain you what is diffeology. You know that already, but I will try to illustrate the definition by what can diffeology bring to differential geometry. So, for example, how to prove that the homotopic invariance of the de Rham cohomology. So this is an exercise, an application of the construction David remind you. So you consider two diffeological space, x prime and x, and a path into C infinity of x prime into x. And now you take a form, a closed form on x, and you consider, and you take closed form, a form in x, which is closed. And now you consider the map big F, which go from x prime to path of x, and to each x prime, I associate the path t goes to ft of x prime. This map is a smooth map for the diffeology involved, and I use a construction. I will talk again after, I will explain again. This is a chain homotopy operator. This is an operator. This is a linear operator that go from the k form on x into the k minus form on path of x. So this is an operator we have to construct. It exists such an operator that satisfies this condition: d composed with k plus k composed with d is equal to 1 star minus 0 star, where 1 is a time 1 of the path, 0 is a time 0 of the path, k is an operator, this is a differential operator. And now you apply that to d alpha, So you have d of d0k alpha plus k d alpha. So you take the pullback by f, you take the pullback by this function of this identity, and is equal to f star 1 star of alpha minus f star 0 star of alpha. So this is 0 by hypothesis, okay? And this commute. So we have d of f star of k alpha is equal, but this is 1, f1 star alpha minus f0 star of star alpha, and this is beta, and you get the result, means f1 star alpha is equal to f0 star alpha plus d beta. And this is the proof. So you see, this is an example of application of how diffeology can help you even in differential geometry, because the category of manifold is a full subcategory. What I have proved here apply exactly in manifold, and you have your proof of homotopic invariance, not true just only for manifold, but for any diffeological space. So instead of repeating the axiom, I want to show how diffeology can be used even in ordinary differential geometry. So, okay, so this will go there. Okay, so now I have to introduce this object. I finish at 30, yeah? I finish as 12:30.
12:20.
20. Okay. Okay. Yeah. Okay. So a diffeological group is a group with a diffeological space with what you imagine it is, and I introduce the space of momenta of a diffeological group to be the space of left invariant one form of the group. I denote it by J star even if there is no J. This is not the dual of Lie algebra. It is defined just to be the vector space of left invariant one form on the group for this multiplication. And I will use that to introduce, yeah, good. This is my part of advertising. So diffeology, you can buy it as a book. I suggest a Chinese reprint, and there is Taiwan and Japan. You can buy it if you're interested in diffeology. Okay. Okay, so everybody knows that we have main object in differential in symplectic geometry is a group of automorphism, a group of Hamiltonian, one parameter group, and the moment map. And this is the space we want. This is the object we want to extend. So the moment map. What is the moment map? The moment map. The simplest case of the moment map is when your form, your parasymplectic form, is exact as a primitive, and the primitive is invariant. So you consider the orbit map. So the orbit map goes to your space into the group, the group into the space by J gives G of X. And you can take the pullback of the form alpha by the orbit map, is give you a map from X to what? To G star, to the set of left invariant one form, and this is a moment map. So the moment map is nothing difficult. It's just the pullback of the one form of the primitive, okay? But of course, not every closed to form has a primitive, okay? And if it has a primitive, it may be not invariant. So the trick is to go up to the set of paths of X, the same way here. So you take K omega is a one form. Since omega is a two form, K omega is a one form, lambda, and you define and you consider the derivative of this K omega, which is a two form now, but this two form is equal to 1 star omega to a star. And if J preserve omega, then J preserve lambda. So you are in this case of the simplest, you are in the simplest case, okay? And you define the path moment map. The path moment map of the action of J, it is a map from the path of X into the set of momenta, and defined by the pullback by the orbit map of K omega. J is equivalent for the coadjuvant action, and psi is equivalent for the coadjuvant action here, and it satisfies this additivity that if two paths are juxtaposable, the psi is additive, because the K is an integration actually. But we are not interested in the path moment map. We are interested in two-point moment map. So we have to push down this moment map. Okay. So we define the two-point moment map to the push down of this moment map. So it is by definition psi of x prime is just the big psi of a gamma that starts at x and finish at x prime. Okay, but of course it cannot be pushed that way. We have an obstruction, and the obstruction is the value of the moment map on the loop, because if you have two paths that go from x to x prime, the difference is the loop. So we have a moment map. We have a moment map that go not into G star, the set of left invariant form, but in some kind of quotient, some kind of torus, but it may be infinite torus and the product of infinite vector space by a torus. And this satisfies, it is still invariant, it is still at star invariant, but it satisfies, it is a Schalke cycle that satisfies this condition, psi of x prime plus x prime is equal to psi x prime. This is a two-point moment, but we are not still happy because we want one-point moment map. So we have to solve this equation. Psi of x prime is mu of x prime and mu of x. It's always possible because x is connected. The general solution of this equation is you choose a point, a base point, and you say small psi x0 x plus any constant. But now the moment map is not anymore equivalent. there is a defect of a lack of invariance, which is characterized by this term. This term is a cocycle. This is one cocycle of J with value in this group, this abelian group, G star over gamma. And this delta here, the delta C is a co-boundary. It's a co-boundary. So we are in a specific case. Sorry, we are in a specific case where we are not in the case of an equivariant moment map, but a theta affine ad star equivariant moment map. Okay, so this is for the moment map. Now we want to go from parasymplectic to symplectic. We start with a closed form, parasymplectic, want to go to parasymplectic, to presymplectic. So for a manifold, to be a presymplectic, it's just a passive Darboux theorem. So the omega is locally such a matrix. So there is a symplectic part and a kernel part, but there is an alternatively, you can see the active version of the Darboux theorem. Just d-flock of M is transitive on M. Okay, this is the d-flock of MW. This is a local diffeomorphism or local automorphism on the closed form omega is transitive, which is equivalent to say that. Okay, this is about the characteristic actually, but I don't care because I have no time to do that. Okay. Yeah. No. This is just to inspire the definition. Okay, maybe I. Okay, I will define what is diffeological vector space, diffeological symplectic space, and I will try to mimic geometry, but I don't want to use kernel because diffeology with kernel doesn't like covariance. So I want to try. Okay, a presymplectic space. Parasymplectic diffeological space will be just a presymplectic if the local automorphism is transitive. So I decide to call presymplectic space a diffeological vector. Diffeological space parasymplectic for which the pseudo group of local automorphism is transitive. This is equivalent in diffeology as in differential geometry, but it's not the same because the model is not given. In differential geometry, you have the model, but here you have no model, okay? But you keep that. Okay, so there is a stronger version, there is a stronger variant, but okay, we don't care about the stronger variant. Okay, and now this is a theorem actually. On a manifold, okay? Now I'm on a manifold, a presymplectic form on a manifold is symplectic if and only if the universal moment map is injective, and this will be the key of defining diffeological symplectic diffeological space. What is a universal moment map? Is a moment map for the whole group of automorphism, which is a diffeological group because we are in diffeology, so you're not constrained with Lie group, so you can consider the whole group of all the automorphism, and this is a theorem. This is a real theorem. And local transitivity and injectivity are necessary because look at that. That is not symplectic, okay? Because there is a degenerescence at 0. But the universal moment map is still injective. But it's still injective. The universal moment map is injective. At 0, the value is 0. But the group of local diffeomorphism is not transitive because at 0, the kernel is the whole space, and any 0 point. So the conclusion of this short analysis is that let omega be a closed form on a manifold M omega, and let omega be a closed form on a manifold M, a closed form. The form is symplectic if that is curve omega is equal to 0, if and only if the local automorphism are transitive and the universal moment map is injective. And this is equivalent to say that it is symplectic, but viewed from the diffeological point of view, okay? From the diffeological. Now that gives the definition of a symplectic diffeological space. A space will be a diffeological space, a parasymplectic diffeological space will be called symplectic if and only if. It is a definition, it's not a theorem now anymore. if it and only if the pseudo group difflog x omega is transitive and the universal moment map omega is injective at most with diffeological discrete preimage, because maybe not injective, but the preimage must not be big because they contain the characteristic actually of omega, the preimage. This is my definition. I mean, the definition I suggest for diffeology. What is the symplectic diffeology? What is a symplectic diffeological space? That kind of space. Now you know that you call symplectic orbifolds are not symplectic in my sense actually, because there are singularity. So we have to add some kind of to consider orbifold, symplectic orbifold. We have to say, okay, a parasymplectic space is said to symplectically generated if there exists a generating family for which omega f is symplectic for all chart. So this is the result of a long discussion with Yael 10 years ago. We have a dispute on what is symplectic in diffeology because this is a long shot, means a long, and she didn't agree with me. She said it's too hard, etc. I want my orbifold to be symplectic, but I cannot accept orbifold to be symplectic because there are singularities. So no, it's not possible. We have to respect Darboux, you know. If we believe that Darboux is intrinsic to symplectic geometry, we have to respect Darboux even in diffeology. There is no way. Okay, you can think about. There is no way to avoid this difficulty, because you betray Darboux. You betray the meaning. No, I'm not joking. You betray the meaning of what is symplectic. So we have to but it's not bad, you know. Symplectically generated, it's okay. We have a generating family of the diffeology, and for each map, the value of omega is symplectic. Okay, so this is.
Actually, that's exactly what it is in money, because you say that symplectic money is something that has a symplectic action.
Yeah. Yeah, absolutely. This is more equivalent. Yeah, but the fact that we change the definition of symplectic form by these two main properties, to be injective and to be transitive, means that you have to understand a different. Okay, let me.
True question there.
Okay, yeah. No, because I have no time. I want to finish. So there is the two examples: the cone orbifold, the cone orbifold. Now the cone orbifold. This generates for the cone orbifold. I didn't write it. Okay. This form generates the standard form on C. It generates the two form. Generates the two form on every two form on the cone is a projection of a coefficient. Okay, whatever. The corner orbifold is not symplectically generated. So the cone orbifold is symplectically generated because it's a pushback to forward. Why I didn't write? Okay, the corner. Okay, the corner orbifold. The corner orbifold is generated by the map pi x y x2, and the value of omega in this pi is just 4xy the x dy, and the C is not symplectic, and which is not the case for the corner orbifold, which is a standard form. So the cone orbifold is symplectically generated, and this one is not symplectically generated. So you can do something even with this. Okay, example of a moment map. So I said the moment map is a one invariant one form on the group. Okay, so the first example, the moment map is a differential of the Dirac function. Mu of QP is just the differential of the Dirac function. The Dirac function, the Dirac distribution on C infinity is not a distribution; it's just a function. It's a value function. Okay, so this is the moment map, for example. This you can compute. Now, for the set of one form on sigma, and this is what Nanko just talked about in the previous. She said the moment map is a curvature here. Well, moment map is not the curvature. As in this picture, moment map is not a curvature because the curvature is not an invariant one form of the group, but the moment map is a distribution made with a curvature. So you find again the curvature, but not as a kernel of the moment map, okay? Okay, this is a distribution. The action of omega on itself, the moment map is just the concatenation of d beta. And here again, the moment map is a distribution with a test function to be one form. And the vector space is symplectic in the sense above because the group of automorphism is intransitive because it is intransitive on itself. And the moment map, you can't compute that it is injective. So the symplectic, what you call symplectic, the symplectic form Nanko just talked about is symplectic also in the sense of diffeology. Okay. This is a good example, a nice example. This is an example I have done myself at the moment. Everybody was talking about Virasoro. So you take this form. I said this form dividing by the speed make impossible to extend to the whole set to the whole C infinity of S1 in R2. Okay, you divide just to be not extendable to the one, and you can compute the moment map. This gives you this formula. The formula where I never see the formula anywhere else than in my paper. Okay, well, okay. No, but this is not. Maybe this is interesting. Maybe not. I don't know. But what is interesting is the computation of the lack of the Soyoko cycle. In this case, this is a Schwarzschild derivative. So what is interesting is that maybe the moment map, it doesn't talk much to us because we don't know that stuff. I mean, it's okay. But the lack of equivariance talk much more because this is the Schwarzschild derivative, and this is the cocycle. So by extension of the symplectic of the parasymplectic form, we get the central extension with the cocycle. I didn't write the name. I forgot the name of all mathematicians now. I'm quite old, and it's a cocycle of what? Yes, there is two names. There is two names, the extension, whatever. Okay, sorry. Okay, symplectic reduction. So let's consider the reduction of a contact manifold. So you have a contact manifold. So curl lambda intersection curl d lambda is equal to 0. And you have the rep vector field, which is defined by lambda psi is equal to 1 and d lambda psi is equal to 0. The theorem is the following. Let lambda be a contact form of a manifold Y. There always exists a space F of characteristic. There always exists on the space F of characteristic of d lambda a parasymplectic form omega such that class c'est le quotient, c'est l'application quotient. It's a quotient map. Okay. Class star, the pullback of omega is just the derivative of the pullback of this parasymplectic form on the space of characteristic if the exterior derivative of the contact form. And if S is a manifold, then omega is symplectic in the usual sense. But if S, the set of characteristics, is not a manifold, is more complex, is a more complex diffeological space, it still exists a closed form, and the dimension of the quotient is 2n. Dimension in the sense of dimension of the sense of diffeology, and the quotient space is symplectically generated because you can take symplectic slice of the rep fields. So this apply for it doesn't work anymore. Sorry. Zoom is not connecting. I have a problem with Zoom. Why have a problem with Zoom? Of course. I talked too long, no? Join a meeting. Okay. I'm sorry for this interruption, but my computer, my Zoom on the computer doesn't, Lynn is not here. Okay, maybe I have to quit Zoom because I don't remember by heart the. Okay, Zoom. So can you repeat me the number, please? 994 2904 6192, and it's okay with that, and okay, and okay.
It's okay. Close that.
I close that. I close. Continue.
Okay. And then speech.
And share. And the desktop. And I close.
Video panel.
And video control.
And you're okay.
And I will again? Yeah, maybe. No? Oh, yes? Oh, no, this is my fault. Okay. This is just because I was not. Okay, so, I'm sorry for this interruption. Where I was? Okay, so this is it, huh? Okay, so I think this is it. So this is another example of singular reduction in infinite dimension. You take the periodic form with the periodic function with value in C, the set of Fourier coefficient. You have this action, and then you have the moment map here. You can compute the moment map. The moment map is the energy dot dt, and the energy of F is just the sum of the square root of the Fourier coefficient pondered by the coefficient alpha n. And if you look at the infinite sphere with parameterized by alpha, which is an ellipsoid, an infinite dimensional ellipsoid, we can study the orbit of R on this ellipsoid. The singular orbit are the harmonic of the harmonic, the only harmonic. So you have an infinity of circle, which are the singular orbit, and every other point the orbit is R, because there is no, the stabilizer is 0, so the action is R, because all the coefficients are independent on Q. And the harmonic are the circle of radius 1 or whatever, we don't care. And the quotient space is a quasi-projective space, and the theorem is that the form passes to the quotient and gives to the quasi-projective space a parasymplectic form omega, despite the infinite singular orbit. Now you can connect that with the quasi-sphere, the Elisa-Prato quasi-sphere. You can embed Cn into this infinite space, just you embed naturally, and you do the same trick, and you get all the quasi-sphere. And this space is, in some sense, the universal, the classifying space for quasi-sphere. My guess is that if you extend this action by R key in A, not just R, but R key, and you do the same trick, you get a classifying for toric quasifold, which is a classifying space for toric manifold and toric orbifold, the same thing, and you have the same theorem that the quotient, the form passes to the quotient. Okay, now let's go to prequantization. This is a little bit more new. So, okay, so consider a manifold. This is a manifold with a parasymplectic form. A manifold, you define the group of period of omega as the integral of omega on the two cycle. Okay, the two cycle with value in Z, and you define the torus of period as a group, the quotient group R over P omega. This is where diffeology acts very precisely, because this space is in general not a manifold, and even in any other extension of differential geometry, this space is more or less trivial. Okay, it is not trivial only if it is integral, but this is for every group of period. Okay, theorem, there exists a T omega principal bundle, Y over M, equipped with a connection from omega of curvature omega. This is a generalization of the prequantum bundle, the classical prequantum bundle, when the form is integral. Such integration bundle are classified up to equivalence by the group of extension of the H1 by with value with coefficient in the group of period. When omega is not integral, it means when P omega is not just proportional to Z, it's not a Z inside, then T omega is an irrational torus, but Y is not manifold anymore, but it is a diffeological space, and everything is nice. So this was for manifold. Now there is a construction. What happens when you leave the manifold and you go to the general symplectic, parasymplectic diffeological space? So this is a theorem. Let X omega be a symplectic connected parasymplectic diffeological space. Let the group of period defined by the integral of K omega on the loop of loop. This plays the role of the H2. And let's define T omega as a quotient space of R, the torus of period. Then define on path of X, pointed X, the equivalence relation. Gamma is equivalent to gamma prime if gamma prime, if they have the same end, and if the integral of K omega on the path connecting the constant loop to this loop, gamma connected with the inverse of gamma star. Oh, sorry. You have X, you show the point X, and you have a point X prime, and you have gamma, and you have gamma prime, and you consider the loop L gamma connect gamma prime bar. This is this loop, and you integrate the one form on a loop, and this gives you an equivalence relation if this computation, if this value, if this number belong to P omega. Now, the theorem says the quotient Y of path XX by this relation is a T omega principal bundle for the concatenation with the loop at the and projection, and the projection pi class gamma is gamma of 1, and the one from K omega project on Y into a connection from lambda of curvature omega. That is this figure. Oops, sorry. That is this picture. So for every simply connected space, diffeological space, even if it is a reduction actually, even if it is a symplectic reduction, you take a manifold, you take a manifold, you reduce by a moment map, etc. You have a parasymplectic space, but this space is quantizable. Okay, if it is simply connected, because I didn't solve the whole question, I'm still working on the non-simply connected case, but this is, I can discuss the point after if you want. So every symplectic, every general, so this is integration bundle, this is a general prequantum bundle. General in two senses. General because the group here is not a manifold, it may be an irrational torus, and the space here may be singular, maybe infinite dimensional, whatever it is, this works. Okay? So there is something, so this is a quotient of space of path. Okay, the real picture is to forget what? To forget X and to build the groupoid as Nantkur said previously. I work with groupoid actually, but if I want to compare with quantization, I have to compare with a fiber bundle. But this is, in reality, I build a groupoid with all the paths, which is interesting because whatever, I keep that for discussion. I want to finish because I still maybe 7 minutes, 7 because of the interruption. Global analysis. So we have to define what is a Hamiltonian diffeomorphism for a general diffeological space. Okay, I pass to the definition. You can find on the book. What is interesting is that symplectic manifold are coadjuvant orbit. Okay, so the whole framework of diffeology can help you to understand what is how to say that, what is intuition for every mathematician knows that. I had this intuition that every symplectic manifold is a coadjuvant orbit because the group of Hamiltonian symplectomorphism is transitive. So, but this is okay. We can prove that, completely prove that in the framework, but this is more interesting, is this one. Because yeah, It is a symplectic orbit, but it may be not affine, not equivariant. For a symplectic manifold, this may be not, you have not, it is not, the moment map may be not equivariant, the universal moment map, and you have a coadjuvant action, which is an affine coadjuvant action. So for every symplectic manifold is a affine coadjuvant orbit. But you can make the affine coadjuvant orbit a linear coadjuvant orbit because the manifold has this quantization, prequantization, whatever the group of period is, this is what is important. Now you can consider the group of automorphism of lambda, or the connected component. It is a central extension of the group of Hamiltonian diffeomorphism, and the kernel is just the torus. Yeah, but I prefer not to. I prefer to call it automorphism because it's a kind of a generalization of quantification. I can discuss no, it's a problem. There are open problem behind that. Okay, quantization is quantization. You need to have a circle if you want to have holomorphic, for example. When you have T omega, even any T omega, it does. There is no circle. There is it's something else. I don't know. Whatever. So this is the group of automorphism. Well, yeah, okay. This is you can call that quantumorphism if you want. Okay. This is a generalized quantumorphism. It's an extension of Hamiltonian by T omega. So you have a moment map here. You have a moment map from d lambda. D lambda is a moment map which go into A star. And this is equivariant because, you know, because I said you are in simplest case where the one form is invariant. Okay? So this is invariant. This moment map, because this is central, group is central, this moment map passes to the quotient. So you have a quotient space, which is mu bar m. Okay? And this you have a push down of the moment map, and you have a map mu m, which is a lifting of the moment map from the last slide. And this moment map, which is with value in the momenta of this extension, this moment map, this is linear. This make m be a linear coadjuvant orbit. You absorb the default, the lack of invariance into this extension. And so every symplectic manifold is a linear coadjuvant orbit. This is typically diffeology, okay? This doesn't work if you are not in diffeology. You can prove that, you can understand that without diffeology. Intuitively, it's okay. But to prove that, you need to have a structure on T omega. A structure that is taken into consideration by the geometry. And if you say, okay, I will restrict myself with a Fröhlicher space, for example, it doesn't work because this is trivial for Fröhlicher space. You need, okay, maybe there is another theory than diffeology that will englobe that, will contain that, and you can do that. But okay, so that's all for.